What's the definition of slope? Huh? No, it's not an angle. The slope is the tangent of this angle, but you guys don't want to do trigonometry, do you? So think of a basic definition of slope that you've heard since, I don't know, 7th grade. The rise over the run. Okay. And what's my run right here? 1. So what's the rise? If the run was 1 and the rise was 1, then the slope would be 1, wouldn't it?
Yes.
Okay, the slope is m, and the run is 1. So what's the rise? M. M certainly equals to m over 1. And I've indicated for you here that the run was 1. So this is your refresher on what happens with a line, okay? And these are all of the parts. M and B, they are numbers. We decide what they are from the outset. And then X, you pick some number you like for X. You can put it in and compute what the corresponding value for Y would be. And that describes what all of the ordered pairs look like on this line. They all satisfy this equation. And what we are going to do is we are going to have a data set that has a bunch of points, and almost surely those points would not exactly be on a line. Maybe those points are like this. And maybe they are something like hours spent studying and the grade on the test. Just for example. And so that point right there has some information, like maybe that person spent 5 hours and got an 80. And so it makes a bunch of ordered pairs. And what we are going to do is try to have a line that is as close to all of the data points as it can be. And that is what we will call linear regression. Here's the attendance code. So this is the big idea. And there's a particular definition of the line that does this. And in order to talk about it, we have to recall some things. What is a deviation? What was a deviation? Where did we use deviation already in this course?
Standard deviation.
Okay. And when we developed the standard deviation, how did we get that? We couldn't use the average deviation. We had to do this standardization procedure to turn it into a standard deviation. And what did that entail? What did we do? What other statistic that we covered in here does the standard deviation come from? The standard deviation was equal to,
Square root of the variance.
the square root of the variance. And what was the variance? In words.
Complicated. It was like a bunch of numbers.
It is a bunch of numbers, but it does not have to be complicated. If you can understand why we had to use, why this is called the standard deviation and not the average deviation, and it helps to make it not complicated if we know this. What is a deviation?
Deviation is something that's strayed away
From the mean, from where you'd expect it to be. It's the distance from the mean, the signed distance. So if it's above the mean, it's positive. If it's below the mean, it's negative. So we'll see some particular point and subtract away the mean. And this tells you how far away from the mean you are. Because a distance is a difference, right? Here's 3 and here's 5, and how far apart are they? They're just two units apart, and the computation for that is a difference. It's the big number minus the small number. It gives you the number 2. So if the point that I'm observing from my data set is bigger than the mean, then this will be a positive number. If this is smaller than x bar, it would be a negative number. And in either case, it's going to tell you how far away from the mean you are. That's a deviation. The variance was where we added up all of the squared deviations. Every single data point is going to have some deviation. And if we just tried to take the average of the deviations, we always got 0. So we had to square them. We had to square them, that way they were all positive. And when you added up all those squared deviations, in an attempt to take an average, we divide not by how many data points there were, but by one less. And that's having to do with your degrees of freedom. If you think about how we calculated degrees of freedom, it was n-1. And it's for the same reason we're having to divide by n-1 in the variance. Otherwise, if we were just dividing by n, if I just divided by n, then this would literally be the average of the squared deviations. Now, isn't it much easier to say average of the squared deviations than to look at it and see this huge bunch of numbers and symbols The variance is as close as we can get to the average of the squared deviations. But for this n-1, it would be. Now, because we squared it, we kind of got to undo that. And so we take the square root here and call it the standard deviation. Let's look at this. I want to focus on the numerator of the variance. That's what that is in the box. That's the numerator of the variance, right? So if I have a data set, now it's one of these data sets where the points are ordered pairs. So maybe it's hours spent studying and it's the grade on the test up here. And we might expect that if you don't spend very long studying, you might make a low grade, but it won't be a perfect correlation. Some people might spend a long time studying and still not do as well as they would like. Some people, like this person, might not study very much at all and still make a great score. But for the most part, the trend is upward. Positive, so that the more time you spend studying, then naturally we would expect you to get a higher grade, up to some point of diminishing returns. Now, let us suppose that somehow I knew that this line was my regression line. The regression line has other names, like the best fit line. That's a popular name. There's at least one more. The regression line, the best fit line. Oh, I know, the other one. I'll save it for in a moment. Now, a deviation was previously how far it was from the mean, but in a more general sense, it's how far away from, I mean, in an everyday sense of anything, it's how far away something is from what we expect. So, if I've told you that this is the regression line, then somehow I have an expectation that my data would follow this line. I can get a deviation of each one of these points by just measuring how far away that point is from the line. Each data point will have a deviation indicated by this green line. And as you can see, this one here is negative. It's below what we expect. This one here would be a positive deviation. It's literally this distance. That one there is pretty tiny. It's positive. This one's negative. This one's positive. This one's positive. If it's above the line, it's positive. It's coming out higher than what we expect. And what was that numerator that we were focusing on? The sum, I said add up here, it's the sum of the squared deviations. Right? Somehow we used that property to standardize what the expected deviation should always be. The sum of the squared deviations. I can do the same thing here. Each one of these deviations is some number. I'm going to go ahead and make up some numbers to put here. So maybe this one is -2, and this one's probably 3, and this is 0.02, and this one's -1.5, and this one's 0.5, and then this one's also 0.5. Each one of these points had a deviation from this line I'm insisting is the regression line. Then, I can now tell you the definition of the regression line. It is the line, there's just one of them, whose sum of squared deviations is minimized. Our objective was to have a line that was as close as it could be to all the points, whatever that means. And we're going to have this tell us what close means. We're going to have this idea tell us what close means. And you could see that such a line would have to be oriented like this, because if I drew any other line, maybe this one, then you could come through here and start measuring deviations. We would have to measure this one and square it. We would have this one that we'd have to square. We'd have this one we'd have to square. And by the time I got all these deviations measured, squared, and added up, can't you see that the number I would get would be much larger than the one that I would get for the yellow line? Yeah, much larger. Because all those red lines are way longer than the green ones. So the regression line is going to fit as close as it can to the data points, such that the distances from each of them, if you squared them, added them up, it's as small. No other line has a smaller sum of squared deviations than the regression line. And some people had to do some very interesting work to produce this line. It takes some higher end calculus to get it done. to uncover what it must be from scratch. So obviously we're not going to do that, but instead, this is the official definition of what it is. And you can reason out that it must be something like this yellow one because it can't be the white one for the argument that we gave. The red deviations are way, way more. And we want the sum of all those squared deviations to be minimized. That'd be like saying we want the numerator of that variance to be as small as it could be. And in turn, since the standard deviation came from the square root of the variance, then it would have a standard deviation that was just as small as it could be. But we don't divide by the number of points or anything. This is the official definition. And this regression line, oh, I forgot to tell you the third name. The third name is the least squares line. And you can see why it would be called least squares, because that is the definition. It's all the deviations squared, add them up. The best fit line is the one with the smallest sum, the least of the sum of all the squares. We can use the best fit line to make predictions. With an asterisk next to this. Because here's the problem. Even though that line comes very close to what all our data points are, such that I might be curious, well, if someone spent, this amount of hours, maybe this is 3 hours, then I could kind of predict what score they might get on the test by just using the y value that I would get on the line when I put a 3 in for x. So in that sense, we could make predictions. Obviously, it would be a little bit off right here, but this is probably the best prediction I could make, even though this deviation here is kind of big. However, the best fit line will not always be the best predictor. It is just a predictor. And here is a case for where it would be a bad one. Maybe I have a data set that is all mixed up. It looks really random, and I'm looking at this data set, and I can't tell if it's got an upward trend or a downward trend, sideways. I really don't know. Doesn't it look just like random? It would be much different from a trend like this, where we can see that these points are kind of going up. Now, just because it's got this random appearance, you can still mathematically generate the best fit line. There is still going to be exactly one line such that all of the deviations, all of the squared deviations are minimized. suppose it was this one. It's not very obvious to me that that should be my best predictor. Even though this line might be the one where all of these lengths are as small as they could be when you add them up. It's a pretty good predictor right in here, but it's just getting bad on the ends. You know? The least squares line will not always be the best predictor. It's just one of the predictions you could make. Even though that line right there might have the least sum, this line here might have a sum that's this much different. And the yellow one just barely beat it. The yellow one could have just barely, by 0.0001, beat the sum of the green one. Okay? So with that in mind, we can't always assume straight away that the best fit line is what we should use to make our predictions. Can you think of, if you had a data set like this, can you think of one other way to give a prediction for what you think the Y value should be? Let's stick with the hours is on the x-axis and the grade is on the y-axis. And what you want to do is for this many hours right here, maybe this is 3 hours, I want a prediction of what the grade might be. I want a strategy to determine what the grade might be. In the event that we have something like this where the best fit line is simply calculable, not necessarily the best predictor. I need another way to make a prediction on what a grade might be. Each one of these points, this one has a grade, I don't know what it is, it's an 85, this one's a 70, and each one of these points has a grade, and you know them all. Take the average. That's an excellent predictor. It was our first predictor. It has the effect that no matter what I put in here, I'm going to get the same prediction, right? And it's a perfectly fine predictor. Now, this is our y-axis, so the average I would call y bar, not x bar. Y bar, that's the average of the y values. It'd be the average grade. The best fit line will be called y hat. The best fit line will be called y hat. And the average, since it's an average of the y values, is y bar. And we will have a hypothesis test to tell us which one to use. There will be a hypothesis test that tells us, okay, you have strong evidence to use the best fit line, or your evidence is awful for that best fit line, in which case we would use Y bar. But we need to know more about how this is calculated. How do they get that equation of the best fit line? Well, it starts off with deviation. We know what a deviation is. The deviation is, I pick some point from the data set, I subtract away its mean. But our data points aren't just numbers anymore, they're ordered pairs. So there's also a y-coordinate to deal with. You have your data set, it is a bunch of ordered pairs because it makes that plot of all the points. And each one of those ordered pairs has an x-coordinate, has a y-coordinate. And to find x bar, I would take the average of all the x-coordinates. To find y bar, I take the average of all the y-coordinates. So then each coordinate has a deviation. The x-coordinates have deviations, the y-coordinates have deviations. And when we talked about deviation, the next thing we built was the variance from the deviation. We did that by, what's the word? What is the variance? Sum of the squared deviations divided by n minus 1. Well, we've got two things going on here, x values and y values. We have to do a covariance. The covariance is very similar to the variance. Because for the variance, you would have said, okay, I have the first data point and I subtract away x bar, and you would have squared it, and you have your second one. Here, I'll write it like this. Instead of putting the 2 for the squared, I'm just going to put them the same thing multiplied again. That's what squared means, right? So this is the first deviation squared, because there's 2 of them multiplied. I would have the second deviation squared, and so on, until I got all the way to the end of my data set. That's why that's a little n, because you have n many things in your data set. This was the first one, this was the second one, or sorry, that was the first one, this is the second one, so on and so on, and then that's the nth one. And since each one of these is squared, then I'd be ready to do my variance if only I would divide by n minus 1. Now that right there, that is the variance of x. To produce the covariance, I'm not going to square them, but I am still going to have this product of 2 things. It's just that the other one will be the y-coordinates. and that's the covariance. It's not really different from, I mean, it is different, but it has the exact same structure as the variance. Instead of the stuff being squared, it still has this product of two terms, but we get the y one involved. Okay. That's our covariance. We built it out of the variance, or excuse me, we built it out of the deviations. And then what we do is we define this new number. This is a lowercase r. It's called the correlation coefficient. Correlation coefficient. By definition, it is the covariance of x and y. That's how you indicate the covariance. Divided by the product of each of the standard deviations. So you have a standard deviation for just the x coordinates. You have a standard deviation for just the y coordinates. You multiply them together, that's the denominator. It gives us the correlation coefficient. Now, what does this number do? First of all, it is trapped between -1 and 1. It can never be outside of this range. But it could be -1, it could be positive, it could be 0, or it could be any number in between. We have to know how to interpret the situation depending on where this r value is at in between -1 and 1. So, I draw you some pictures. If my data set had a plot that looked like this, by the way, we would call this a scatter plot. I think we did that in week 2 or week 3, something like that. Then in this case, R is positive and R is close to 1. It's close to 1 because look at how tight of a grouping it makes up near that line. The points are close to the line, so the R value is close to 1. It must be positive because what is the slope of this line, positive or negative? So the R value is positive because the slope of the line is positive. It's not close to 0 and positive. It's closer to 1 than it is to 0 because of how close the points are to the line. If, on the other hand, the points were very far away, but still we got this line, Well, it would still be positive, but it would be a lot closer to 0 than it would be to 1. So maybe in this first example, R is 0.85. And maybe in this second example, R is 0.25. Okay? Based on these two pictures, could you imagine what happens if R is negative and close to -1? Well, first decide what's going to happen if R is negative. You can do that. What's it going to be like if R is negative? It would slope down. The slope of the line would be negative when R is negative. So you'd have data points that are kind of going downhill. And we'd have the same sort of situation down here. If R was negative but close to 0, well, the data points would be all spread out. But if it was negative and close to -1, then they'd be real close to the line. It's just that the line would be going down. And finally, what would be the situation if R was exactly 1 or exactly -1? Huh? No? No? No. Look at the behavior of the points as it changes from being close to 0 to close to 1. And then surmise what would happen if it was exactly 1.
Would all the points be exactly 1?
Yes. If the R value was exactly 1, all of your data points are exactly on the line. And if R was -1, then it would be sloping down and all the points would be exactly on the line. So what happens if R is equal to 0? If when it's -1 or +1, the points are right on the line. What's going on at 0? What's going on if R was equal to 0? There's always a best fit line. We can always compute a best fit line. It's just a matter of, will that best fit line be worth looking at? No matter how scattered out my data set is, there's going to be one of these lines whose sum of squared deviations is smaller than any other line. But it might not be the case that that line is worth using. It might be the case that the average is doing a better job of making the predictions for us. So what happens when the R value is 0?
Would they all be directly below it?
Mm-mm.
They will share the y-axis or the x-axis.
It will be something like this. The points will be as far away from being on the line as they could possibly be. If the R value is equal to 1 and the points are all on the line. And if it was -1, they're all also on the line. Then when that R value is as far as it can be from -1 and 1, that means it's at 0. So correspondingly, the data points would be as far away from the best fit line as they could be. It would, in other words, your data set is as scattered and as random as it could be. Change any one of the points, and it would be less random than it is right now. Okay? When the data set is all randomized, scattered about, we can still produce that best fit line, but it isn't going to help us. So in a situation like this, we would have R equals 0. There's no trend. In the other cases, you had a trend. The data points are going up or maybe down. They might be kind of far or really close, but in either case, there was a trend. When you have something like this, there's no trend. It's just boom, random. No trend. R is 0 means there's no identifiable trend. And R is a regular letter from the alphabet. Here's what I see. A lot of times students, they'll see this symbol and they'll think I'm writing the square root symbol. No, this is a lowercase r. I wish I could do better. I'll put a little. It's a lowercase r. And it makes the R sound. And then you know how these mathematicians do. They got to have, if you're going to talk about a mean, they're going to use a mu. And if you're going to talk about a standard deviation, they're going to use the sigma. So this R value, it comes from our sample data. So it is a sample value. The Greek character that looks like a P but is not, it is a rho. Is the correlation coefficient for the population. It's the correlation coefficient for the population. A number that we won't have access to, just like in most cases we can't get the population mean or the population standard deviation because it's just too hard to do. However, we are going to do a hypothesis test involving rho that will tell us, should we use the best fit line? Should we use the average of the y values? And that hypothesis test is, it's always the same hypothesis test. It's rho is equal to 0, or rho is different from 0. Now, since rho is the correlation coefficient of the population, its behavior is still the same as R, right? It's trying to measure the degree of the correlation to see if there's any trend. And suppose we failed to reject this hypothesis test. I failed to reject. So my evidence cannot support this one. We forget about this one and we have to go with this guy. And it's telling us that the correlation of the population, what is this going to mean? What did it mean for R? So here, same thing. You have this random, your population has no trend. If the population isn't going to have any trend, then I should not be using the best fit line. If I fail to reject, that means I'm stuck with this one. And I would have to use y bar. So if I fail to reject, I'm going to have to use y bar to make my prediction. However, if I reject this guy, then I have evidence to support this one, that the correlation coefficient for the population is different from 0. Now, I don't know if it's positive or negative. All I know is that it's not 0. That means there is some trend. It might be small, but at least it ain't nothing. There will be some kind of trend. And if there is some kind of trend, then the best fit line will do a better job than y bar at making your prediction. So if we end up rejecting, we would need to use the best fit line. And that's the hypothesis test. Okay, so we saw where the definition of this silly line. We know what it means. It needs to be close to all the data points, and this is how we're measuring close. We're going to use it to make predictions, but it isn't necessarily the best one. We had to introduce this thing called covariance in order to give a meaning for this R value. We are not actually going to compute an R value by hand. It's too involved, too many opportunities to make a mistake. It's possible, that's the formula, but we're not going to. And finally, that best fit line, y hat, it's got to be equal to some kind of mx plus b. How are they getting the m? How are they getting the b? Well, I'll tell you. The m is equal to the r value times the standard deviation of the y values over the standard deviation of the x values. That simplifies to be the covariance over the standard deviation of the x values squared. And this b winds up being y bar minus m times x bar. You're not going to use any of this stuff to write down a formula. Instead, I hope you can appreciate the automated tool that we're going to use that's going to give us these numbers, so that way we don't have to do all this, because this is kind of a lot. It just involves using this covariance, and if you think a little bit, this covariance has in it the information about all those deviations, and it's used, the slope is relying on that R value, and that's kind of why if the R value was negative, well then this is going to be negative, but if the R value was positive, then this is going to be positive, because both of SY and SX have got to be positive numbers. They're standard deviations. They're never going to be negative numbers. Finally, if you want to compute the B value, the place where it crosses, look at what's involved. X bar and Y bar. Of course, you need M first, but what does this mean? This tells you that your best fit line goes through the point X bar comma Y bar. The best fit line goes through the average of the x coordinates and the average of the y coordinates. So it has on it the average of the x coordinates, the average of the y coordinates as an ordered pair. Well, naturally, you would expect that to happen because it's trying to make predictions, and the average is a pretty good prediction. Take the average x value, it should give you back the average y value. That's all it says. And this is how they build that line. You need all this stuff. What we are going to do is we will end up using utility in StatCrunch if you go to stat, if you click the stat button and you click regression, and then simple linear, that's what we will do every single time to produce the R value. Here's what we get out of this. We get the R value. Now, I'll tell you, in StatCrunch, they call it capital R. They're wrong to do that because capital R has another job in statistics. It's busy doing something else. The thing that they are calling capital R is, they call it capital R squared. I don't know why they used a capital R. They shouldn't have. It should have been a lowercase r. But have that in mind. It's still the correlation coefficient. We will also get the best fit line equation. They will give it to us. We will also get a scatter plot of our data points with the best fit line plotted on top of it. I won't have this problem in here because we're a face-to-face class, and I'll be standing right here when we do the signature assignment together. But it sure would be nice if word got around to future students that that this computation is really involved. But we don't do it by hand. We're going to use StatCrunch. So whenever students hand me in their signature assignment, and it has a whole bunch of computations different from these to get the R value and the slope. B is still done the same way, but these aren't the only ways to get these done. They're just the most concise. Can you imagine that this is the most concise way? There's a much more elaborate way to get this R value. And almost every semester, someone will turn in a signature assignment that has the crazy long way of doing the R value. And what must I think has happened in every time that happens? Huh? No, they hired someone to do it.
Oh, they cheated. Oh, interesting.
Yeah. Because the person that they hire, they know exactly how to do it. You can go to a website, you can pay $200, you can give them the sheet, and they'll do the whole thing. Right? But when they do it, it's extremely obvious to me. right? And I don't think that the students really realize that. It's so obvious that, you know, this technique wasn't used, first of all. Second, we never did it in here this way. And every time we did it with StatCrunch. And the instructions I provide insist that you use StatCrunch to do it. So, like I said, it won't be an issue in here because we're all going to do it together. It's like really no problem. We're going to have so much time on that we're going to be able to do the final and the signature assignment and probably leave early because there's just not, that's just all there will be done at that point. It doesn't take that long. What takes so long is building up to what does the R value mean? How do I use it for this hypothesis test? The fact that you may use, there may be cases where the average value is used instead of the line. And but now we've got all that out of the way, we are ready. When we come back from our break, we'll be ready to do the problems. There aren't even that many problems for this week. How many is there?
7.
Okay. Some of them are real short too. So there's not a lot to do. This week's going to be easier than you think. Next week, be even easier. And then after that, we'll be in week 9. We'll do the final, we'll do the signature assignment. And then there will be a week 10 meeting, but it's on Zoom. We won't do much there, but we'll do something. And you'll have to turn in something for points. It's only 30 points, but there'll be something in week 10. We'll talk more about that later. What's up? I don't know. I forgot. I'll have to look it up. I think it's around about the same time. You can see it in your student portal if you look. But I'll check and let you know. All right. So when we come back, we'll do the homework. Then we'll be out of here. Divine.
It shows for me it's due today. Like on my phone, it shows the convention's due today, but it was due last night when I checked on my computer. So I don't know.
It's due last night.
This is what I get in May 16. Let me see the couch. Like May 16 today at 1 Pacific time. Yeah. But today is the 16. Today is the 16, yeah.
At 1. Yeah. Even like, that was like this morning at 1:50 something.
I'm thinking, I don't know, for some reason I thought we were gonna take it in class.
Did you not take it?
No, I thought we were doing, I guess I'm confusing it with my other plans that we're taking into in class. I thought we were doing it today, like in the summary, like on your phone, it says May 16th, so I was like, okay, we're gonna do it in class.
No way.
So I was thinking we're gonna do it in class today.
Usually we set up with the final because he said.
Or maybe, yeah.
Yeah, because last time he did do the whole rundown, and he did say that we were gonna take the final in class.
It'll be okay. Just explain it to me.
Yeah, that's fine. I could take it like after class.
Okay. We've got some pairwise data, X values and Y values. We've got a button to open it in StatCrunch. That's what we're going to do. Let's see, what is this data? So this number is the percentage, so this is some particular country. This is some particular country, and it says that 79% of people are internet users, and that 5.4 in 10 million of people in that country win scientific awards. Can you imagine what type of correlation they're trying to show? They're trying to inspect, is there a correlation between your country having a high amount of internet access and if the people in that country win scientific awards? We might think that the more internet access you have, the more predominant it is, then maybe the more scientific award winners you would have. That's probably what they're thinking. And the first thing that we'll do is open our data in StatCrunch so that we can do the stat regression simple linear. So it opens the data, it even names the variables, internet users, award winners. Stat regression simple linear. The X variable is always the first one. The Y variable, always the second one. And you don't do anything else. It's got a lot of options. You don't need to touch any of it. You just hit compute. And it gives us a 2-page summary. On the first page, there's a lot of numbers. Second page is the picture. So this is looking like you'll have more scientific award winners if internet use is more prevalent in your country. The first question they ask us is to identify which graph it is. So there's just 4 choices, and if you make your image kind of square, then it should match the perspective that you see in your answer choices. And so I just have the one possibility. Only the one that would match mine. Then they want the R value. And like I said earlier, the R value is not a lowercase r in StatCrunch, it's a capital R, and it's right there. correlation coefficient. To 3 decimal places for me, 0.809. They want me to do the hypothesis test. It's always the same. Rho is equal to 0, or rho is different from 0.
You said it's always the same?
We always have the same question. Is the population have no trend at all, or some trend, no matter how minor? No trend at all, some trend. This hypothesis test needs a test statistic and a p-value. It's right here. So to 2 decimal places, I have 2.75.
Can you tell me how you chose
You
that?
got them in the bottom, right?
Yeah, how did you choose that?
How did I choose it?
Why did you choose that one at the top? Because it says slope.
That's just the one that we want.
It's just the one we want.
Because the slope is the slope is what's determining the trend. Right? So whatever that slope is directly related to are the points going up, they're going down. And that's the only one we'll use. If you forget which one it is, you can know because down here they also have a p-value. And that is our p-value. It's the same one that's right here, so you have this test statistic that goes with it. So my p-value to 3 decimal places, 0.051. Now my significance level, alpha, is just 1%. So this p-value is too big for our preference. So we are not safe to reject. There would be a 5% chance of us being wrong if we reject, so we would fail to reject. Because the p-value is greater than the significance level, we do not have the evidence to say that there's a strong correlation. Because when we failed to reject, that was when we had to use y bar, not the least regression, not the least squares line. Okay, that's the whole question. Do we have number 1 done? No. time, or can you help?
I didn't get the line.
The second question is pretty much the same, but then after that they'll change theme. Here it's ages of acting award winners matched by the years in which the awards were won. So each one of these columns is a different year. So in this year, the sector was 49. They're trying to see, is there a correlation? Like if we knew what the age of the best actress was, could we accurately predict the age of the best actor? What do you think? Is that a correlation that seems plausible?
Yeah.
Why is that?
Because I'm looking at the, maybe I'm wrong, but I'm looking at the graph and the plots aren't too random.
Okay. Has there ever been a year that you could think of when the best actress was relatively young and maybe the best actor was kind of an old guy or something? I mean, it can certainly happen. But there's really no reason that I can think of to say that their ages should somehow correlate. Most definitely they're not necessarily in the same movie. Maybe if they were always in the same movie, then I could say, well, this movie is about, young people or something. And so they would both be young. Or maybe this movie in the other year was all about some older folks, in which case they'd both be older. But it's not necessarily the case that I could think of that they would be, that their ages would need to change relative to each other, such that if the best actress got older, then the best actor would also need to get older. If I open my data in StatCrunch and go to stat, regression, simple linear, X variable is always the first one, Y variable is always the second one. Let's look at our R value here. Negative 0.36. Is that close to 0 or close to -1? Is it closer to -1 or is it closer to 0? The halfway point between 0 and -1 is what? Huh? Negative 0.5. You know this. It's negative 0.5. That's the halfway point. And so, is it closer to -1 or 0? Right there is negative 0.5. And over here is minus 0.36. It's closer to 0 than it is to -1. And what was that supposed to indicate?
There's no trend, no identifiable.
It's more random than it is got a trend. Right? It's leaning more random than it is leaning more strong trend. If I look at the picture, it made a best fit line. It's going down. It's just because the R value is negative. But there's just one point here that it seems to even be close to. And this thing is supposed to be making predictions for us. I mean, maybe it's kind of close over there, but the rest of them are pretty far. You know, maybe these two are close, but the rest of them just stink. And we can see that stinkiness in the R value being so far away from -1. Let's answer our questions now. First thing they're going to ask is, which graph is it? And if I kind of square this thing up, then I can see, just by looking at some of the important points, which graph it would have to be. So like it can't be D because of that point that's down there. You know, I'm looking at this point up here is going to indicate to me it's got to be this one. Okay, the correlation coefficient is right there, minus 0.360. The hypothesis test is always the same. It's rho equal to 0 or rho different from 0. Test statistic and p-value. Look at that p-value. 0.25. 25% chance I'd be wrong if I reject H0. That's this one. This one says that the correlation of the population is not there. And I don't wanna reject that one. 25% chance I'd be wrong. So I'll fail to reject. That means I'm keeping this one. And this one is the one that means no correlation. We would use the average in order to make our best prediction. All right, so my test statistic is minus 1.22. Yeah. Right, the bottom. Is that 2 decimals? P-values rounded to 3 decimal places. .250. And once again, it's greater than the significance level. I don't even need to check what the significance level is, because it surely ain't bigger than 25%. So there's not any evidence to say that we have a correlation. Should we have even expected one? No, just like we talked about earlier, they appear in different movies. We shouldn't expect their ages to be correlated. That's question 2. This is question 3. There's nothing to open and stack crunch. And this idea here of these critical values, I don't remember if they even ask a question where this is used. But this notion of the critical values of the correlation coefficient is an older alternative to the p-value method. We'll only use it if they insist, but we don't need to and shouldn't here, because we have a p-value. Here they're trying to say, is there a correlation between the IQs of twins? If I knew the IQ of the twin that was born first, could I use that to predict the IQ of the twin born second? That's the thinking. We don't even have the data here, but we've got the summaries. We know the average IQ of the twin born first. We know the average IQ of the twin born second. Right? They've got 20 sets of twins. Look at my R value. It's pretty close to 1. It's 0.87. That's pretty strong. That's a lot stronger than like a 0.3. So I'm expecting these data points, whatever they are, I can't see the graph, but I know that they're pretty close to that trend line, and that this trend line is positive. So that as the IQ of the youngest twin increases, the IQ of the older twin also increases, because the trend line is positive. And it's not a loose trend either, it's pretty strong. In fact, looking at this p-value, says that there's a 0% chance that I'd be wrong if I reject the null hypothesis. Well, what is the null hypothesis? It's that rho is 0, and I don't want that, I'm rejecting it. That means that I think there is some correlation in the population of twins. So since there is some correlation, we would want to use the best fit line to make our prediction. You won't always use the best fit line. You have to check the p-value to know, should I have used the best fit line, or would I just use y bar? In this case, we're going to use the line because the p-value is so low. Now, I have this regression line. Okay. It's looking like this. And I'm supposed to put in an IQ for the youngest twin of 92. right there is 92, and I'll plug it into my equation and be able to look at the prediction for the IQ score of the older twin. Where that other IQ score is, minus 23.27 plus 1.21 times 92. Oh, by the way, in statistics, for whatever dumb reason, they don't say y equals mx plus b, they say y equals b plus mx. It just had to be different. So that's why it's written like this. That's b, and this is mx. So I get 88.05. Oops, forgot my zero. That's the whole question.
Can you repeat what you did right there with the 92 comma? What did you do to get 88?
If I have a line, the equation of my line, let's say, is y equals b plus mx. Points on the line have the ordered pair x comma y, right?
Mm-hmm.
But why is this?
Mm-hmm.
So that means points on the line have the ordered pair x comma b plus mx.
I see.
You take the x value, you run it through the equation, you get the y value. Yes. That's an IQ of 171. That seems kind of high. That's like way beyond genius level. The IQ of the younger twin was 100, or this is husband and wife. The IQ of the husband is 100. Okay. You need to look at this and see how this is different from what they've told you. I mean, is this up here the same thing as that equation? 15.08 plus 0.87 times 100? Well, no. Look at this here in front. You're not adding 15.08 like they are. You're adding 100 minus 15.08. That's why it's so big. Well, what do you have written here? No, this part. Look at that equation. It says 15.08 plus 0.87x, right? 15.08 plus 0.87x. This stuff up here was not asked for. Yeah. So let's get the right number. 15.08 plus 0.87 times the husband's IQ. Now, naturally, we expect the wife's IQ to be bigger than the husband's IQ. And indeed, we get that. I know she's got to be smarter, but not like smarter than Einstein, unless I'm trippy. But I don't even know how high up the IQ scale goes. I think it's 160s. I don't remember.
And this equation, I got the answer right, but there's no need, all this was just a lot of information, it's all fluff to distract you, a lot of that information wasn't necessary, was it? I mean, obviously.
Yeah.
We didn't need to go to the coefficient R chart. I'm confused with that.
I mean, if they only gave you exactly what you needed to do the problem, then it would be too obvious that, oh, I'm going to use the equation, or oh, I'm just going to use the average. Like if I said the p-value is 0.5 and the average of the y-values is this, you're done. Those are the only two numbers you're going to need.
So we didn't need to know whether or not we were going to reject it or not. It wasn't important.
We absolutely did. That's how we knew to use the line
Okay,
or the average of the y-values.
that's right. So we use, we reject or to know which, can you tell me again which equation besides the y hat?
The other one is y bar.
Okay.
Yeah, it's the average. It was our first. It was our first
To find those. Fine.
most rudimentary way to make a prediction. It's just the average.
It's very clear.
There's another one. Here they're trying to see, is there a correlation between the height of an adult male and their weight? For the most part, there probably should be. If you're 8 feet tall, you're going to weigh more than someone that's 5 feet tall. You just have to. For the most part, right? You could be really, really skinny or something, but for the most part, it's going to increase. Now, this R value, that's not really that far away from 0. Right? It's a whole lot closer to 0 than it is to 1. So the correlation is positive. It is the case that as height increases, weight increases, but it's not that strong, at least in this sample of 100 people. It's not that strong. And looking at the p-value, p-value is pretty low. It's just not low enough. There's a 1.7% chance I'd be wrong to reject this. That may seem slim, but it's not less than my significance level. The significance level determines the maximum amount of risk I'm willing to take, and we've broken that. We're bigger than that with our p-value, so I should fail to reject. I'm going to keep this. Since I failed to reject this idea, does it mean that I should use my regression line, or no? I should use the average of the y-values, which is written right here. And so my prediction is that if the male is 158 centimeters tall, their weight will be 81.45 kilograms. I would have made that prediction no matter how tall they were, according to this p-value. So in this problem, I couldn't use my best fit line. I have one, but it's not, the correlation is not strong enough for me to be using it. Get it? These problems are the number one missed problems on the assessments after this. I mean, in the online class, they have a quiz. Guaranteed a bunch of people will miss it over there because they'll think, I need to immediately use that equation of that line. But you don't. You need to check the p-value to see if you should use that line, or if you should use the average of the y values.
My problem is not too far from yours. I don't understand why mine is wrong.
Okay.
I'm confused.
What's your p-value?
Oh, I see. My p-value is 0.007.
Okay, that's going to be lower than your alpha. P-value is lower than alpha.
Yes.
Then that's low enough for you to confidently reject. And if you reject H0, it means you take this idea here and you say, forget about it.
Yeah.
That's not true.
Yes.
Instead, this must be what's true. And what does that mean? That means there is some correlation. So when this happens, you're going to use your equation of the line.
Why didn't you? Your number's not
I
that
didn't
far.
here because my p-value,
Yeah.
it's small, but the boss
Oh, yours is
says it's not small
0.01.
enough.
I'm sorry, yes, mine is 0.05.
I think there's one more question like this.
It's probably useful.
Like I was saying, these are the number one missed questions. Well, I guess there's not one more like it. They just had 3 and 4. And it's totally random. You shouldn't expect one of them to be with the line and one of them to be with the average. They might both be with the line. They might both be with the average. There's no trend that I can detect. It's completely random. All right, here we have just some data, not even a story to go with it. I'll open the data in StatCrunch. I will find the regression line. I go to Stat, Regression, Simple Linear. X variable is the first one, Y variable is the second one. That's all you do, and you click Compute. And what they want from us first is the equation of the line. And you be careful because they want it in the order P plus mx. There's my line. 2.8 plus 1x. Couldn't get a simpler slope than that. Okay, so I've given them the equation of the line. You can also get the equation of the line off of this graph because you can hover over that line and it'll show it to you in a little box. And if I make this kind of square, then right? Instead of the data points being strongly in a line, they kind of make this curve. Right? And if you needed to fit, so linear regression, obviously we're dealing with a line, but I can do polynomial regression. I can fit a parabola to it. I can fit a cubic to it. I can fit any polynomial I want to it. I can do an exponential function fitted to it. I can do a logarithmic function fitted to it. You can do, there's one more, a logistic equation. The logistic equation is just the one that goes like this. At any rate, if I needed to examine this data probably a little better, I might fit it with a parabola, be able to make some other stronger predictions, because the line is just going to go like that. Identify the trend. The data has a pattern that is not a straight line. That's it. I can still use that line to make predictions, but there would be, the point is that there would be an even better option than the average, and the line would be a polynomial. In fact, if I just go and pick polynomial regression, it's exact, isn't it? And look at this R value. It's R squared, but it's R. R squared is literally R squared. So 1 squared is 1, that means R was 1. And that indicates that they're perfectly on the curve. This time it's just a curve instead of that line. So there's all types of regression out there. Linear is just one of the types. Okay, there's question 5. All we have left is 6 and 7. They should be largely the same. It's a bunch of data. Give me the equation, make the prediction. And you can't just haul off and use that line to make the prediction. You have to look at your p-value. They're not even going to ask you for the p-value. You just have to know to look at it. Here we have bears. Their weight and their chest size. So naturally, run into a big bear, has a huge chest, it's probably going to weigh 500 pounds, 528 pounds. But if the bear has a smaller chest, 41 inches, it's only a 300-pound bear. Okay? Open the data in StatCrunch. Stat regression, simple linear. I get my X and Y variables. Or X variable is the first one, Y variable is the second one, and now I have my 2-page summary. There's the picture, and they want the equation. Well, this is it. It doesn't say Y and X, but something went wrong here. Hold on. Chest size should have been first one. Yeah. Chest is X, weight is Y. Weight is Y, that's why it's right here. So it literally says to you Y equals B plus M, and the chest size is X. Look carefully, if you have any negatives, they need to be included. So my equation is minus, let's see, round to 1 decimal place, so minus 330.4. Plus 16.3 X. It's coming from right here. And then they ask me, what is the best predicted weight? I don't know. I need to use my p-value to determine if I should use that line. Well, this p-value is really, really small. It's going to be way smaller than my alpha. My alpha is 0.05, and this is hundreds of times smaller. So I'm safe to reject. So I'm going to use the line. And they want to know the weight of a bear whose chest size is 40 inches. So I'm going to compute minus 330.4 plus 16.3 times 40. My prediction is that it would be 321.6 pounds. And the last question, the last part of this question, they're asking, is your prediction close to what actually happened? They're telling me that they went out and found a bear whose chest was 40 inches and that that bear actually weighed 292 pounds. The problem with this question is that we don't have a definition of close. I don't know what they mean by close. So I sort of have to just look at the answer choices and make my best guess. They've given me the options of not very close, exactly the same, very close, and close. Well, I'm going to say, well, first of all, it's not exactly the same. I would go so far as to say it's not very close. I mean, that's almost 30 pounds difference. Now, I'm predicting the weight of a bear. 30 pounds might be close. You know, if I was predicting the weight of a monster truck and I was within 30 pounds, that'd be really close. It's a bear. I don't know. Do they mean 30 pounds is close? I believe that they're saying 30 pounds is still kind of far away. And I don't know what the cutoff is for close and very close, not very close. They haven't told me, so it's more or less an educated guess. You kind of look at what you have, you see how far away your number is from what they say it should be. They say what actually happened. For me, it's about 30 pounds. On the one hand, it seems kind of close, but not really. It's actually about 10% off. So I went with not very close. For the last question, we are back to the Best Actress and Best Actor's ages. We remember what happened last time. Last time it wasn't a strong correlation. I'm not expecting it to suddenly be strong here, but we still need to go through the motions. We'll open the data in StatCrunch. Stat regression, simple linear. Best actress, best actor. Click compute. And here I have my equation. Now they have some careful rounding instructions here. They said for the y-intercept, round to 1 decimal. So that would be 52.8. And for the slope, use 3 decimals. So that's negative 0.1897. So that'd be 190. Because the 7 rounds the 9 up. The 89 goes to a 90. And now make a prediction of the best actor's age if we know that the best actress was 30 years old. So I'll go to my p-value. My p-value is almost 33%. That's a pretty big risk of being wrong. Most definitely it's bigger than whatever my alpha is. So I would not want to reject age 0. I would not want to claim that there is some correlation, because there's not. It's weak. So I'd be saying there's no correlation. I'm keeping the null hypothesis, keeping age 0. That means I should use the average of the y values.
So just saying you failed to reject?
Yes. I'm failing to reject because the p-value is so big. It would be a very high probability of me being wrong if I reject it. So I'm going to not reject. That means I should use the average of the y values, not the equation that I just found. So I'll go to summary stats columns and get the average age of best actor. That's all I need. Whatever the average age of the best actor is the answer. That is my prediction. I would have made that prediction no matter the age of the best actress. And that matches with what we expect. If we expect that there's not a correlation, then the estimate for what the age of the best actor is should not depend on what the age of the best actress is. Right? The best actress could be any age, and the age that we'll pick for the best actor will just be the same. Round to the nearest whole number, so that would be 45. Now here they do justify what does it mean to be close. They say, is the result within 5 years of what actually happened when the best actor was 51, when the best actress was 30? Well, no. 51 is more than 5 years away from 45. That's the end of the assignment.
Can you show me in StatCrunch for the correlation? For some reason I'm doing something wrong. Can you show me how to get to that?
Get to what?
The stat correlation?
Stat regression simple linear?
No, the last one you just used, the correlation.
No, I did summary stats.
Summary stat.
Columns. Stat, summary stats, columns. I wanted the average age of the best actor. Like I said, the online class has a quiz on this, but the face-to-face class does not. There is no quiz. There is no quiz for this material and for next week's material. The only place you see this getting tested over is on the final, and it gets used on the signature assignment. So if your homework is done, then you're done for the week.